Welcome back. Today we're going to be deriving Euler's identity, a very fundamental formula in mathematics and complex analysis, and really a very beautiful and useful formula. So that will be the end goal of today's work. I'm going to outline what we're doing in this video. In today's video, we're going to begin by rederiving Taylor series. We're going to review what they are, and I'm going to show you another derivation for Taylor series. And this derivation is maybe a little bit more approachable than the derivation I showed you in the first video before this one. Then we're going to actually exhibit some Taylor series. So in the last lecture, we got a general formula for a Taylor series, but it was enough material for one video. Today we're going to exhibit Taylor series, and specifically Maclaurin series, which are Taylor series that are centered at 0. We're going to derive Maclaurin series for sine of x, cosine of x, and e to the x, the exponential function. And we're going to then be able to prove Euler's identity at the end of this video, which is really rewarding. So to recapitulate, Taylor series, this is a review from last time, Taylor series are written when you have a function f of x, and that function is said to have a Taylor series expansion or representation centered at some value x equals a. Let's call it a. And if f of x is shown to be equal to the following, to the convergent series f of x equals f of a plus f prime of a times x minus a, that quantity raised to the first power, so we don't necessarily have to show that, but there it is, plus f double prime of a, the second derivative at a, times x minus a quantity squared all over 2 factorial, which of course is just 2. And by the way, these earlier terms are over 1 factorial, which equals 1, and f of a can be written to be over 0 factorial. I didn't do that here, but that's fine. 0 factorial equals 1. Continuing the series, plus f triple prime of a times x minus a quantity cubed, all over 3 factorial. I hope you're seeing the pattern again to refresh your memory, plus the fourth derivative of f at a times x minus a to the fourth power, all over 4 factorial, plus the fifth derivative of f evaluated at a times x minus a to the fifth. You can see how this approximation is getting better and better. These terms should be getting smaller and smaller, all over 5 factorial, and so on. So that's your Taylor series. And I'm going to show you now another derivation, and this one should be easier by most people's estimation than last time. What we're going to do this time is we're going to assume that the function we're interested in, f of x, has an infinite series expansion. So last time you'll remember we didn't actually assume the existence of the power series. We developed it by a process of repeated integrations. This time we're going to assume that it has an infinite power series expression centered at the point x equals a. And we're going to then show what the coefficients for that power series should be. That's going to be our derivation. So we're saying f of x equals some undetermined constant c0 plus some new constant c1 times x minus a to the first power, plus another constant we don't know yet, c2, times x minus a squared, plus a third constant, a fourth constant, but we'll call it c3, times x minus a quantity cubed, plus c4 times x minus a quantity to the fourth power, plus c5, and this is going to keep going, x minus a to the fifth power plus c6 times x minus a to the sixth power. I'm just really writing this out so you see the pattern, and so on, dot, dot, dot. So that's a general power series, and now we're going to determine what those coefficients should be. So we're going to observe that f of a equals c sub 0 plus c1 times, letting x equal a minus a. Well, those two things just cancel, so this entire thing just equals 0. I'm going to cross that out, equals 0. Plus c sub 2, look what happens here. That's going to be, again, a minus a squared. That term is going to just equal 0. Plus c sub 3 times a minus a. In other words, all of these terms in our series, except for the very first one, are all getting canceled out. They're all going to equal 0. So I'm going to erase them just for simplicity so you can see what we've concluded from this. F of a equals c0. So we've actually found our first constant term in this Taylor series. So I'm going to sub it in there. I'm going to write f of x equals f of a plus the rest of this series that I've written so far. So we're going to keep going, but before we do that, I just want to review some of the rules of differentiation which we'll need to determine these other unknown constants. So the first rule to remember is that if you have a constant times a function, this is of course the constant rule, if you have a function y equals c times f of x, to take the derivative y prime or dy dx, that just equals c times f prime of x. Okay? The second rule to remember is the power rule. And that rule says that if you have a function y equals x to some power n, to take the derivative, y prime, you bring the power down so it becomes n times x to the n minus 1. That's the power rule. And these are all familiar from differential calculus, hopefully. The next rule is another one. This is kind of an easy one, the sum of derivatives. So if you have two functions, y equals f of x plus g of x, to take the derivative, you get y prime equals f prime of x plus g prime of x. So we're going to make use of all of these rules now, moving forward. Well, so far, we've found only c0, but we know c0 equals to f of a in the series expansion. And we wrote it that way. We wrote f of x equals f of a in place of c0 plus c1 times x minus a to the first power, quantity to the first power, plus c sub 2 times x minus a quantity to the second power, quantity squared, plus c sub 3 times x minus a quantity cubed, plus c sub 4 times x minus a to the fourth power, plus c sub 5 times x minus a to the fifth power, and so on. And now we're going to differentiate this function. So for starters, the c sub 0 term is a constant term. It's just equal to f of a, but when you differentiate a constant, you get 0. And then I'm going to use the power rule on all of the subsequent terms in my series. I bring the exponent down, it becomes a coefficient, and the exponent is lowered by 1. So here the 4 comes down and becomes a 3, the 5 comes down and it gets lowered to a 4, and so on. So we now have f prime of x equals 1 times c sub 1 times x minus a raised to the power of 0. But that, of course, all just equals 1 times c sub 1, obviously, plus 2 times c sub 2 times x minus a, now this is just to the first power, plus 3 times c sub 3 times x minus a quantity squared, plus plus 4 times c sub 4 times x minus a quantity cubed plus 5 times c sub 5 times x minus a to the fourth power, and so on. The pattern keeps going. So that's what we get when we differentiate. Now, because that term x minus a to the 0 power just equals 1, I can rewrite it as f prime of x equals c sub 1 plus the rest of that series. Now I can calculate f prime of a, and f prime of a is going to equal c sub 1 plus 2 times c sub 2 times a minus a. We're letting x equal to a, and that term equals 0. And we're doing the same thing, actually, that we did before. We're going to see that all of the subsequent terms, except for c sub 1, cancel out when we calculate f prime of a. So I hope you see the pattern. They're all going to 0 out, and you're left with f prime of a equals c sub 1. Well, that's pretty cool. So now we have two of our constants. We have c sub 0 equals f of a, and we also have found now that c sub 1 equals f prime of a. Not bad. And we can continue this process. We're going to rewrite f prime of x as the following. F prime of x equals f prime of a, we know that's what c sub 1 equals, plus what we found before, 2 times c sub 2 times x minus a to the first power, plus 3 times c sub 3 times x minus a quantity squared, plus 4 times c sub 4 times x minus a to the third power, plus 5 times c sub 5 times x minus a to the fourth power, plus ... and so on. Now let's differentiate this again. We know what to do. We're going to find f double prime of x. The f prime of a term is a constant, so that just becomes 0. It cancels out. And then we apply the power rule again, and we get 1 times 2 times c sub 2 times x minus a, again to the 0th power, which of course just evaluates to 1, plus 2 times 3 times c sub 3 times x minus a to the first power. Remember, bringing the exponent down and then lowering the exponent by 1, plus 3 times 4 times c sub 4 times x minus a quantity squared, plus 4 times 5 times c sub 5 times a to the third power. We're just applying the power rule across all of these terms, plus ... And then what do we get if we want to calculate? Well, I'm just tidying it up first. We get f double prime of x equals this expression. And what do I get if I want to calculate f double prime of a? Well, as we've seen already, we get 1 times 2 times c sub 2. That term is left alone. But then look at our next term. It's 2 times 3 times c sub 3 times a minus a. That's going to equal 0, so that whole term multiplies out to 0. And so do all the other terms that follow it. So we're left with f double prime of a equals 1 times 2 times c sub 2. And I'm going to then say that c sub 2 equals f double prime of a all over 2 times 1, which is the same as saying it equals f double prime of a over 2 factorial. So I hope you're beginning to see how we get the different terms in our Taylor series. So I'm going to just rewrite that series expression, f double prime of x equals 1 times 2 times, and then I'm going to fill in what we know c sub 2 to be equal to. It equals c sub 2 equals f double prime of a over 2 factorial. So the 1 times 2 and the 2 factorial cancel there. And I'm left with f double prime of x equals f double prime of a plus the remaining terms. Now to find c sub 3, we repeat the process again. We differentiate a third time. We're going to differentiate this expression, and we're going to get f triple prime of x equals 0. Remember that first constant term, when you differentiate it, becomes 0, plus 1 times 2 times 3 times c sub 3 times x minus a to the 0 power, which of course just equals 1, plus 2 times 3 times 4 times c sub 4 times x minus a to the first power, plus 3 times 4 times 5 times c sub 5 times x minus a squared, plus 4 times 5 times 6 times c sub 6 times x minus a quantity to the third power, and so on. And then we know what to do next. We're going to find that f triple prime of a is going to equal 1 times 2 times 3 times c sub 3, and all the other terms are going to cancel, setting x equal to a in that expression. Or just rearranging equivalently, c sub 3 is equal to f triple prime of a all over 1 times 2 times 3, 3 times 2 times 1, it's the same thing. Or we could say it equals f triple prime of a all over 3 factorial. So I'm going to write that next to the list of other coefficients we already have. C sub 3 equals f triple prime of a, the third derivative of f at a, all over 3 factorial. And in fact, I'm going to go back and rewrite c sub 0 as f0 of a over 0 factorial, and c sub 1 is f prime of a over 1 factorial, just to be consistent. And 0 factorial and 1 factorial both equal 1. I'll show in a later video why 0 factorial equals 1, but in general, c sub n equals the nth derivative of f evaluated at a all over n factorial. That's our general definition. I'm writing that again here. C sub n equals the nth derivative of f evaluated at a all over n factorial. And now we have our general Taylor series. Our general Taylor series for a function f of x, centered around a point x equals a. So we say f of x equals f of a plus f prime of a times x minus a to the first power plus f double prime of a times x minus a quantity squared all over 2 factorial plus f triple prime of a times x minus a quantity cubed all over 3 factorial plus the fourth derivative of f evaluated at a times x minus a all to the fourth power all over 4 factorial plus the fifth derivative of f evaluated at a times x minus a quantity to the fifth power over 5 factorial, and so on. That's our general Taylor series. So I've just rewritten it up here. Now I want to talk about the Maclaurin series, which is very closely related. We're going to set a equal to 0 now. That's our Maclaurin series by definition. So then we say f of x equals f of 0 plus f prime of 0 times just x, because x minus a, of course, is just x, plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus the fourth derivative of f evaluated at x equals 0 times x to the fourth power all over 4 factorial. And so on. A Maclaurin series is nothing more than a Taylor series where we have centered it at 0, where we have set a in the expression equal to 0. But it does simplify things. So there's our Maclaurin series, and now we're going to use this tool finally. We're going to try to find the Maclaurin series for some functions. And we'll start with the trigonometric function sine of x. So we need to remember some facts about sine of x and recall our formula, which is that c sub n, the nth constant term, equals the nth derivative of f of x evaluated at x equals a over n factorial. But here in our Maclaurin series, a equals 0. So in our Maclaurin expansion, c sub n is going to equal the nth derivative of f evaluated at 0 over n factorial. All right. Now, if our function f of x is sine of x, then we know that f prime of x equals cosine of x. That's just a fact we know about the sine function that we learn in calculus. We know then that if we take the derivative again, the derivative of cosine of x is negative sine of x. And if we differentiate again, the derivative of negative sine of x is negative cosine of x. And finally, when we get to the fourth derivative, we get back to sine of x. The cycle repeats itself. So that's just something that you memorize in calculus. Hopefully you're shown a proof for that, but that's an important fact to know. So then, the Maclaurin series, or the Maclaurin expansion, for sine of x can be derived. We're going to say sine of x equals sine of 0, that's the f of a term, plus, we're going to now take the derivative, cosine of x evaluated at x equals 0 times x to the first power, plus, differentiating again, negative sine of 0 times x squared all over 2 factorial, plus, differentiating again, negative cosine of 0 times x cubed all over 3 factorial. The derivative of negative cosine is sine again, so plus sine of 0 times x to the fourth over 4 factorial. Differentiating, plus cosine of 0 times x to the fifth over 5 factorial, plus negative sine of 0, I just put a minus sign there for efficiency, times x to the sixth over 6 factorial, plus negative cosine of 0 times x to the seventh over 7 factorial. And I think we have enough terms there. So now we're going to simplify this expression. Sine of 0 is just 0, cosine of 0 is 1, negative sine of 0 is just 0, negative cosine of 0 is negative 1. And the cycle repeats itself. So do those terms there. And what we're left with is the Maclaurin expansion for sine of x. Sine of x equals x minus x cubed over 3 factorial. All the 0 terms have canceled out. Plus x to the fifth over 5 factorial. Minus x to the seventh over 7 factorial. Wow, beautiful. I'm just continuing so you can see a few more of these coefficients. They're all odd, right? 3, 5, 7, 9, 11. Which is why we're justified in calling sine an odd function. Cosine, of course, is an even function. And there you have it. I put a box around it. That's the Maclaurin expansion for sine of x. Now, we could utilize the exact same process for deriving a formula for cosine of x, a Maclaurin expansion for cosine of x. That Maclaurin series formula is always usable, but we have a shortcut available to us. We know that the derivative of sine of x, d dx sine x, equals cosine x. That exclamation point is just punctuation, not a factorial symbol. So let's just differentiate the series above to find cosine of x. So we know the derivative of sine x is cosine x, so differentiating term by term, the derivative of x, we're using the power series, but many of you probably know that the derivative of x is just 1, minus, okay, here we apply the power series, we bring down the 3, make it a coefficient, and lower the exponent to 2. And the 3 in the numerator cancels out the 3 in the denominator, and we're left with minus x squared over 2 times 1. Bringing down the next exponent, the 5 cancels in the numerator and the denominator, and we're left with x to the 4th over 4 times 3 times 2 times 1, minus, bringing down the 7 here, lowering the exponent to 6, canceling the 7s in the numerator and the denominator, we're left with minus x to the 6th over 6 times 5 times 4 times 3 times 2 times 1, and so on. So the next term is going to become x to the 8th over 8 factorial, and then the next term after that will be minus x to the 10th over 10 factorial. So now I'm just going to clean up this expression a little bit. I'm going to write 2 factorial there, 4 factorial, 6 factorial. And there you go. Very quickly, we're able to derive the Maclaurin expansion for cosine of x, which, in contrast to the sine function, is an even function. So now we're going to find the Maclaurin expansion for the exponential function for e to the x. So the central fact to remember here is that the derivative, d dx, of e to the x is equal to e to the x. So all of my terms in the Maclaurin series, f of 0, f prime of 0, f double prime of 0, that's just going to equal e to the 0 every time. So I'm going to get e to the x equals e to the 0 plus e to the 0 times x to the first power over 1 factorial, plus e to the 0 times x squared over 2 factorial, plus e to the 0 times x cubed over 3 factorial, and so on. E to the 0 x to the 4th over 4 factorial, plus e to the 0 times x to the 5th over 5 factorial. But remember, e to the 0 with power just equals 1. So our expansion is going to be e to the x equals 1 plus x squared over 2 factorial, plus x squared over 3 factorial, plus x to the 4th over 4 factorial, plus x to the 5th over 5 factorial, dot, dot, dot. So let's do a reality check on this. We know that e to the x is equal to its own derivative, d dx e to the x equals e to the x. What happens if I differentiate this series expression that I've just come up with? Well, if we take the derivative of both sides of the equation, we're hoping that the equation on the right, that the expression on the right is unchanged. So the constant term cancels, derivative of x equals 1, and then when I pull down the exponent, it cancels the first term in the factorial, so that gets reduced by 1. Everything just gets shifted over by 1, essentially, or down by 1. When we differentiate, our series is completely unchanged. So the derivative of e to the x equals e to the x. When we differentiate that formula, we get back the same formula. That's pretty cool. So now we have, from our Maclaurin expansion, e to the x equals 1 plus x to the first over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus x to the 5th over 5 factorial, and so on. And now we're coming to the last section of today's video, which is Euler's identity. The great mathematician Leonhard Euler asked the following very intelligent question. What happens if instead of looking at e to the x, we substitute I times x, the imaginary number I times x, into this formula? So that's a very interesting question. And now we're going to answer it. So we then have, if we plug in I times x into our expression, e to the I times x equals 1 plus I times x, quantity raised to the first power, plus I times x, quantity squared, over 2 factorial, plus I times x, quantity cubed, over 3 factorial, plus I times x, quantity raised to the fourth power over 4 factorial plus I times x to the fifth power over 5 factorial plus I times x to the sixth power over 6 factorial. And I'm going to keep going, and you'll see why in a moment, plus I times x to the seventh power over 7 factorial plus I times x to the eighth power over 8 factorial plus I times x to the ninth power over 9 factorial. I know this might seem a little tedious, but it will be worth the effort. So that one over 10 factorial, and then the next one over 11 factorial plus I times x to the 12th power over 12 factorial. Whew, that's a lot of terms. But you'll see why I wrote out so many in a moment. Here we're going to recall arithmetic fact, which is a times b to the n equals a to the n times b to the n. So then I'm basically going to get rid of my parentheses, and I'll distribute the exponent in a moment. I'm just getting rid of all the parentheses because it's easier than switching back and forth between pencil and eraser in my paint application. But basically, the exponent gets distributed to both of our coefficients there. And now we have to remember an important property of the imaginary unit I, which is that I to the first power equals I squared equals -1. This was in the very first video in this whole series. I cubed equals -I to the fourth equals 1. And then the cycle just repeats itself, right? It just goes round and round. So I can now substitute those numbers in for I raised to all these exponents. So I get there, I squared equals -1. The next term, I cubed, I'm going to erase that. That equals -I. So I'm just going to put a minus sign there instead of a plus sign. That's more efficient. Plus I to the fourth just equals 1. So I'm going to put a 1 there. And it goes around again. So I to the fifth just equals I to the first, which equals I squared equals -1. So I'm going to write a -1 there. I to the seventh, again, just equals -I, so I'll just put a minus sign there. I to the eighth equals 1. And then here we go. I to the ninth equals I to the 10th equals -1. So put a -1 there. Could have put a minus sign there. Either is fine. I to the 11th equals -I to the 12th equals 1. So we have a nice pattern here. Again, lots of patterns in this video. I'm now going to rearrange and group together all of my terms that have I and all of my terms that are exclusively real terms. So then I'll get e to the I times x equals 1 minus x squared over 2 factorial, no I in that term, plus x to the fourth over 4 factorial, minus x to the sixth over 6 factorial, plus x to the eighth over 8 factorial, minus x to the 10th over 10 factorial, plus x to the 12th over 12 factorial. All of my even terms. Plus I times x minus I times x cubed over 3 factorial. I'm grouping together all of my I terms now. Plus I times x to the fifth over 5 factorial minus I times x to the seventh over 7 factorial, all my odd terms it seems, plus I times x to the ninth over 9 factorial minus I times x to the 11th over 11 factorial. So now I'm just going to pull out the I from that parenthesis expression. Sorry about that plus sign, that'll go away. There we go. We got e to the ix equals this top parenthetical expression with all the even terms plus I times the bottom parenthetical expression Well, we should remember what those things are. E to the ix is going to equal the Maclaurin expansion for cosine of x plus, what's down here? The Maclaurin expansion for sine of x plus I times sine of x. So there you have it. I'm going to put a box around this. This is Euler's identity. E to the ix equals cosine of x plus I sine of x. There it is again. This is Euler's identity. Really beautiful formula in math. So I'm going to show you one immediate consequence of this formula, and that is as follows. E to the I pi, if we let x equal pi, equals the cosine of pi plus I times the sine of pi. So sine of pi equals 0, cosine of pi equals -1. We'll move that over to the opposite side, and we get e to the I pi plus 1 equals 0. Just a beautiful formula that brings together all these important constants. Well, next time, what are we going to do? We're going to start with the polar formula, or polar form rather, of a complex number using Euler's identity. We'll then discuss something called the roots of unity. And then finally, we'll move on to talk about the complex sine and the complex cosine formulas. Well, that's it for today. Thanks for watching.